Okay, so hello all. So today we'll be discussing about the topics that were covered in the week 10. So in week 10 we have talked about the characterization of isolated proteins products part 2, in which in lecture 1 we have studied about the sequencing of biomolecules, overview of protein sequencing, breaking disulfide bonds. Just a minute. Yeah, so in the lecture one, which is about protein sequencing, so we have talked about the different techniques or the different ways of sequencing of biomolecules, then the overview of product sequencing, then how the bisulfide disulfide bonds can be broken. So when we are doing any kind of sequencing, so first step is to reduce the disulfide bonds. Why? Because if you're not reducing the disulfide bonds, then what happens that it will interfere in the protein sequencing process. So therefore it is the first step during protein sequencing process. Correct? Okay. After this, we have talked about, now that we have broken the disulfide bonds, then comes the cleaving of the polypeptide chains, and then finally the sequencing of the polypeptide chains. So as we always do, first what we'll do is that first we'll just quickly revise what we have studied in the last week, and then we'll come to the questions, and then we'll solve the questions, right? So one by one we'll go through each lecture. So in week 10 we had three lectures. So first we'll see lecture 1, and then we'll talk and then we'll try to solve the questions of lecture 1, and then we'll go to lecture 2, and then we'll solve the questions of lecture 2, and like this we'll just sequentially move. Okay, so up till now what we have studied is that in downstream processing you have your product. Okay, you have isolated and purified your product. We are talking about protein product mostly. Okay, so now you have your protein product with you. You have your product with you. Now you want to characterize it. Now, what is the meaning of characterization? So, if you know that in when suppose at molecular level when you have a sequence, so what you do is that you do annotation of the sequence. Okay, if you have heard of this term annotation. So what does annotation signifies? Annotation tells that assigning property to that particular sequence. What is the location of that sequence, what that sequence symbolizes, everything. So in the same way, whatever product that you have got through downstream processing, you want to characterize it, as in you want to determine its properties. Like you want to determine what is its molecular weight, you want to determine what is the sequence of that particular protein, and then what are the functional groups that are present in that protein, so that you have information about that protein. Okay, you want information of the product. Okay, so now for having the information of the product, you need to know about its molecular weight, about its sequence, about the functional groups that are attached, so that you know what kind of product you have isolated. Or if you knew that I wanted these properties in my products, that you know that you have isolated the correct product. Okay, so now if you have to determine the molecular weight, how you can determine the molecular weight? You can determine molecular weight with the help of gel filtration chromatography or electrophoresis. You can determine sequence with the help of some sequencing techniques that you will be studying in subsequent uh, uh, in this class only. And then some functional groups, you can determine functional groups with the help of some spectroscopic techniques such as IR and UV visible spectroscopy. Fine. So gel filtration chromatography, we can determine the native molecular weight. But with the help of electrophoresis, we can determine native as well as the subunit molecular weight. Now, what is the meaning? What is the difference between native and a subunit molecular weight? That native molecular weight means that the protein is as a whole. Okay, it is not being denatured, or the disulfide bonds are not reduced. So you have just one complete native protein that you have isolated. But when your protein goes through under denaturation conditions, with the treatment of beta mercaptoethanol or SDS, then what happens? The different subunits of the proteins, they get broken off. Okay, so protein is not a single entity, as we all know. Protein is made up of different subunits. Okay, so and different subunits can have different molecular mass. Okay, so just I wanted to tell you how you can differentiate between native and a subunit molecular, what is the difference between native and a subunit molecular weight. So if your native protein is, let's say, 60, okay, and it has three subunits, and these three subunits, it can have either same molecular weight. If same molecular weight, then how many? 20, 20, 20. Or it can have different molecular weights, 10, 30, 20, or 30, 10, 20, anything. So these are the subunit molecular weight, and this is the molecular weight of the whole protein, native protein. So native protein, if I'm talking about a native protein, then it is a protein which is not broken, or which is not reduced. It is not reduced to its subunits. So your native protein subunit weight you can determine with the help of gel filtration chromatography. Okay, but if you want to know how many subunits are there and what is the weight of each subunit, then you can go for electro sorry, excuse me, electrophoresis. How? Because so electrophoresis can also be done under native conditions or SDS, that is denaturing conditions. So native electrophoresis means that denaturing conditions are not provided, whereas SDS SDS polyacrylate gel electrophoresis means that SDS is a detergent. I'm sorry for my extremely bad handwriting. So basically, SDS, it denatures the protein and it imparts negative charge. Fine. So what happens that when you are using denaturing conditions, then you use beta mercaptoethanol or dithiothiotol. Either you use beta mercaptoethanol or DTT. So what they will do is that they reduce the disulfide bonds. Fine. So now what is happening? The disulfide bonds are reduced and your subunits are released now. So now you can know how many subunits are there. So if there are 4 subunits, so you will get a band at their respective weight in your gel. And likewise, you can determine the weight of those subunits because you have a ladder. You have a reference ladder. Okay. So that's what they were saying here, that product characterization, first thing is molecular weight. Okay, then second one is sequence, and the third one is functional groups. So and functional groups can be determined with the help of infrared or UV visible spectroscopy, and you can also determine the native and subunit molecular weight of the functional groups. Now comes the question that why it is important to know the functional groups. So if I'm talking about product characterization, okay, lecture 1 is about product characterization, in which you need to know the molecular weight, you need to know the sequence, and you need to know about the functional groups present on your protein, right? So functional groups are a characteristics properties of a protein. So they are like, you can say they are like the fingerprint of a protein. So therefore functional group characterization is utmost important. Now in this we have first talked about, oh sorry, I don't know why this happens always. So first we'll talk about the sequencing. So when you are doing the sequencing, your first step is to reduce the disulfide bonds. Okay, so after the reducing of the disulfide bonds, you can go for the sequencing process. And for sequencing, you can do Edmond degradation. Okay, so we can have Edmond degradation and Sanger sequencing both. First, we'll study about Edmond degradation. So in Edmond degradation, what you do, that first of all, if there are any disulfide bonds, you reduce the disulfide bonds, and then you cleave your sequence and you try to overlap so that your sequence is established. Now, first step is the disulfide bond breakage. Now, the disulfide bonds can be broken by two ways. First way is by using performic acid, and second way is by using dithiotritol. So when you are using performic acid, you are actually reducing the oxidizing the disulfide bonds. Okay, you can see over here there is SS and you are oxidizing them. So your performic acid is basically oxidizing it. So your disulfide bonds are broken off. Here what you are doing, you are reducing them. So with S either your O can be attached, or with S either your hydrogen can be attached. Either oxygen can be attached or hydrogen can be attached. So that this bond is broken, and this basically what we have to do is that this SS bond, okay, disulfide bond has to be broken. Therefore it has to bound with someone else, something else. Either it can bind with an oxygen or it can bind with a hydrogen. If it is binding with an oxygen, it is done with the help of performic acid. Therefore for breaking of the disulfide bond, the first way is oxidation by performic acid, or you can reduce the disulfide bond with the help of dithiotritol. But when you are reducing the disulfide bond, it is very important to note that you have to make sure that this reduction is not reversed. Okay, so what happens that there are chances that this disulfide bond can be reversed. Okay, so that means again it can form the disulfide bond. So in that case you have to treat your this broken two subunits with iodoacetate. Okay, iodoacetate. So then there is no reformation of disulfide bond. So in the case of oxidation, there are no chances of reformation of disulfide bond. But when you are using the reduction method to reduce the disulfide bonds, to break the disulfide bonds, then there are chances of reformation of disulfide bonds. So in that case, you have to treat your reduced subunits with iodoxidase. So basically, you are doing a carboxymethylation reaction. So what is a carboxymethylation reaction? Carboxy means carbonyl group. You can see C double bond O, and methylation means CH2. So you can see instead of S, which is bounded to only H, now S is bounded to CH2 C double O. That means carboxyl methyl group is added now. Now because this carboxyl methyl group is added, there are very less chances, or say no chances, of the reformation of this disulfide bonds, because earlier there were very much chances that this H2 can release and this again can form the disulfide bond. But now you're treating it in such a manner that now this methyl group and carboxyl group both attached to your S. Okay, so now there is no reformation of disulfide bond. So reduction can be done by DTT, that is dithiotritol, or you can use beta mercaptoethanol also. Okay, so the first stage when you are doing a protein sequencing is that you have to break the disulfide bond. Is it clear? Okay. Now we come to the next step. Your next step is, after that you have broken the disulfide bond. Now what you have to do? You have to cleave the polypeptide chain. Okay. Now how you can cleave the polypeptide chain? You can cleave the polypeptide chain with the help of some proteases or chemical reagents. Okay. With the help of some enzymes. What kind of enzymes? That cleaves proteins. What are those called? Proteases. Okay, proteases, or with the help of some chemical reagents. Okay, so these are some of the enzymes which can be used for the cleaving of the polypeptide chain. You can use either trypsin, chymotrypsin, pepsin, CNBR, but you have to be very specific of which enzyme you, or which reagent you have to use. Why? Because each enzyme is specific to a particular cleavage point, and it will come cleave at that particular cleavage point only. It is not going to cleave at any other cleavage point. For example, if I talk about trypsin, then trypsin will cleave after lysine or arginine. Okay, so if there is if there is lysine or suppose arginine is there, and anything is there, say so it will cleave here. Trypsin will cleave after your arginine. So like this, you have to remember that each and every this thing enzyme has a particular specific amino acid at which it cleaves. CNBR is important because CNBR cleaves after methionine. So this is important for examination point of view also, and in general also for your competitive examination point of view also, your CNBR is important. Then we come to, now we have cleaved the polypeptide chain. So basically you want to our main objective is to sequence it, right? Now for sequencing it, you have to make sure that your polypeptide chain is in a linear form. That's why you have reduced the disulfide bonds. Then you have to cleave the polypeptide chain. After the cleaning of the polypeptide chain, you have to sequence it. Okay. Now a general principle of sequencing which is followed. I mean, this is a general logic, a general concept which we follow for the sequencing of proteins, and that is that for the sequencing of polypeptide chain, you have to cleave the N-terminal amino acid. That means what happens if, suppose, I'll just show you. This is a basic principle, right? This principle will be used in both Sanger and Edmond degradation. So if this is your polypeptide chain, and this is your N-terminal, and this is your C-terminal. So there will always be an N-terminal amino acid and C-terminal amino acid which is present at the extreme end, and then these, suppose these rounds represents each amino acid. Okay, just for your convenience, I'm drawing it in such a manner that each circle represents one amino acid. So what I will do is, for the sequencing, I'll first cleave it. I cleave this bond. So what this is, now I have this is C. Suppose this is 1 2 3 4 5 6 7 and so on. So this was 1, this is 2 3 4 5 6 7 and so on. This is cleaved. Now I will identify this. So I know now that the first amino acid is arginine, say. Now this will become my last nth amino acid, matlab n terminal amino acid. Again I will cleave it. So it would be 2 plus the whole chain. Now I know this 2 is lysine. Then again I will cleave it. So like this, in sequential manner, you will keep on cleaving the N-terminal amino acid, and you will identify it, and then you will, like this, you will get the information of all the amino acids which are present. So this type of sequencing, which starts from the N-terminal by cleaving each N-terminal amino acid, this type of sequencing is known as N-terminal sequencing, because you are cleaving the N-terminal amino acid. Okay, you can also do it in the reverse manner, as in you can also do it from the C-terminal. Suppose that this is my polypeptide chain. Okay, each circle represents one amino acid, as we talked about. Fine. This is your N terminal, this is your C terminal. I am marking it 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14. If I am doing an N terminal sequencing, then what I will do is that I will cleave first this, then this, then this, then this. Okay, from the N terminal. If I am doing a C terminal sequencing, then I will cleave first this, then this, then this, then this, and so on. Is it clear now? How your N terminal and C terminal sequencing differs? Okay. Now, by utilizing this concept, the reagents that are used, that you can learn. Okay, that there is nothing to explain about the reagents that are used. The important thing is that you should know how it is done, the basic logic. So first is, you will first identify the N terminal residue, and then you will label the N terminal residue. Okay, after the labeling of the N terminal residue, you will hybridize it so that it is removed. Hydrolyze it, sorry, you will hydrolyze so that the N terminal amino acid is removed, and then you will identify what the N terminal amino acid is. So for this, you have different reagents that you have to use, that you can study. I'm just revising it here. You have already studied, you must have studied in the class. Now we have two kinds of sequencing techniques for this. First, we're talking about the Edmond degradation. So in Edmond degradation, what happens? Edmond sequencing. So basically, first we have studied about Sanger sequencing. So in Sanger sequencing, the reagent that reacts with the terminal amino group is phenyl isothiocyanate. Okay, I'm sorry. So in Edmond degradation, yes. So in Edmond degradation, the chemical or the reagent that reacts with the terminal amino acid is phenyl isothiocyanate. And in your at Sanger sequencing, the reagent that reacts is Sanger reagent. So what I'm trying to say here, if you're getting a little bit confused, so for the sequencing of proteins, we have two different approaches. Okay, I am talking about protein sequencing. We have two approaches: Sanger sequencing, Edmond sequencing. So in both the sequencing, first there is a reagent that reacts with the N-terminal amino acid. Here it is known as Sanger's reagent. Here it is known as phenyl isothiocyanate. Okay, this is. Then the N-terminal amino acid is cleaved, and the whole step is you can just read it out. There's nothing much to explain over here. You just have to read and understand the basic logic that I've already told you, that first the N-terminal amino acid is removed and then it is sequenced. Then you can also have sequencing from the C-terminal amino acid. So from the C-terminal amino acid, basically the most common method which is used is with the help of carboxypeptidase. So carboxypeptidase basically releases the C-terminal amino acid, and therefore you can do the sequencing from the C terminal end as well. Now, not just that we can have Egmont degradation and Sanger sequencing that we can do, or we have C terminal sequencing also that we can do. We have other methods also, like mass spectrometry method. So mass spectrometry method is again a very popular method, and it is used for the determination of amino acid sequence, and it is fast. Okay, it is a little bit more advanced method. It is fast also. So nowadays people usually try to go for mass spectrometry as well. Okay, so now we'll have completed the first lecture. So now we'll just solve the questions of the first lecture first, and then we'll quickly move to the second chapter. Okay, so your first question is, The first step in the sequencing of protein is A. Cleavage of the proteins with trypsin. B. Cleavage with CNBR. C. Reduction of the disulfide bonds. Or D. None of the above. So what is the answer? What is the first step in sequencing of the proteins? What we do? We first reduce the disulfide bonds. So the answer of the first question is C, that is reduction of the disulfide bonds. Second question is disulfide linkage are oxidized and reduced by. So we have studied that to reduce the disulfide bonds, we can either go for oxidation or we can go for reduction. So oxidation is done with the help of performic acid and reduction is done with the help of DDT. And you can also use beta mercaptothenol for reduction. Okay. Okay, next question is, okay, I'll just do it in this mode. It would be easier for you to understand. Right. So next is reformation of the disulfide linkages can be prevented by A. Decarboxylation by iodoacetate, carboxylation by carboxyl methyl cysteine, oxidation by performic acid followed by carboxymethylation by iodoacetate, or none of the above. Think what should be the answer. Those who are watching it on YouTube, you can also think of what can be the answer of this question. I'll give just 1 minute for you to think. Okay, so what we do is we perform carboxy methylation. Okay, so we do carboxymethylation. So carboxymethylation is performed by iodoacetate. Iodo acetate. But what we have studied just now that when this carboxymethylation by iodoacetate is required, it is required only when we are doing the reduction process of destroying the disulfide bonds. When we are using either DDT or when we are using beta mercaptoethanol, beta mercap, then only we require to use the carboxymethylation by iodoacetate. Otherwise it is not needed. So decarboxylation, no, decarboxylation is not at all used. Carboxylation, no, it is not used. Then oxidation by performic acid followed by carboxymethylation by iodoacetate. So carboxymethylation we do, but not after oxidation, we do it after reduction. So this is also not correct. That means none of the options is correct. Okay, so the answer of a third question is D, that is none of the above. Okay, next question is cyanogen bromide cleaves the polypeptide fragment from A, upstream of methionine, downstream of methionine, either upstream or downstream of methionine at exactly methionine. So where it cleaves? CNBR, it cleaves downstream of the methionine. What is the meaning of downstream? So what is downstream and upstream? So if you have studied mol bio, then you know if this is your start point, anywhere there it is known as. So if I am saying if this is methionine, so after methionine it cleaves. So what we are saying? Okay, after methionine. Fine. Next question is for the C-terminal sequencing of proteins, which reagent is used? CNBR, trypsin, carboxypeptidase, or all can be used. For those who will be watching it on YouTube, I'll giving 1 minute for you to think. Okay. So the answer is carboxypeptidase. How, even if you don't know the answer, as I always say, that whenever you are solving any kind of multiple choice questions, most important thing is to apply logic, right? Yeah, because why I am saying this? Because see, sometimes what happens that the options becomes very confusing, okay? Or even if the options are not confusing, what happens that you don't know, you cannot understand the question, or you haven't read it. Now here they are saying that for the C terminal, if there is no negative marking, then you can take a risk that for the C terminal sequencing. Now C terminal, if you know your proteins, there is N terminal and there is C terminal. In N terminal there is amino group, in C terminal there is carboxy group. So carboxy group will be cleaved by carboxypeptidase, obviously, from, because it is the name itself suggests that it will cleave the peptide bond at the carboxyl group. So like this, if you apply a little logic, it would be easier for you to answer the questions. Okay, you can take a risk. Now we'll come to lecture 2, which is about spectroscopy. So in lecture 2, we have studied about the spectroscopic techniques and the basics of spectroscopy. So how to study the functional groups in small molecules. Okay. Then first, what is the overview of spectroscopy, and then we have studied about the UV visible spectroscopy. So now we have some questions over here, but before going to the questions, we'll first quickly recap of what we have already studied. Just a minute. Key. Right. And then we'll again come to the questions as we did earlier. Okay? Fine. Okay, just a minute. Okay, so basically molecules can have functional groups. Okay, so now for the determination of the functional groups, so basically you can use spectrometric techniques. Okay, so when we're talking about the overview of spectroscopy, this is your electromagnetic spectrum. You must have studied this in class 12th if you are from CBSE board. So uh, this is gamma, these are gamma rays and these are radio waves. Okay, so what do you think, what would be the energy status of gamma rays and radio waves? Wavelength status, you can see that radio waves has the maximum wavelength. What about the energy status? Think what should be the energy status. Okay, so this formula, okay, so we will, okay, here only I'll just tell you. Energy is given by h mu, which is, and mu is written as c by lambda. So E is equals to hc by lambda. What does it means? That energy and wavelength have reciprocal relationship. That means if wavelength is more, energy would be less. If energy is less, wavelength would be more. That means here radio waves have the maximum wavelength, therefore they will have minimum energy, and gamma rays, they have minimum wavelength, that means they will have maximum energy. Okay, now why I just why I was telling you why I focused on energy and wavelength, because this energy level will determine what kind of spectrometric techniques or spectroscopic techniques that we have exploited. Okay, so the spectroscopic techniques that humans have exploited are based on the energy levels of various waves. Radio waves have least energy, gamma rays has the most energy, UV visible rays has some energy at the middle. So basically, what are we studying in spectroscopy is that any particular photon is at a ground state, at a state E1, which I call as a ground state. Okay, ground state. Fine. Now, when it absorbs any particular any particular molecule, or yeah, any particular atom or molecule or any electron, it depends on the context you're talking about. Let's say any electron only. or any molecule, it absorbs energy. Energy is in the form of packets, if you have studied in class 11th in chemistry. So it absorbs a packet of energy, a photon, and then it goes to a high energy state, which is E2. That means, suppose we are hungry, okay? So when we are hungry, we are at a lower energy state, we cannot do work, we are very lethargic, we don't want to study also. So we are at the even stage, but as soon as we eat something and take some rest, we become completely excited and truly fresh to work. So that means we come at an excited state, E2, okay? And then again we do some kind of work, and then again we come back to the lower energy state, again we need food and rest. So same thing is happening over here also. The molecule is absorbing some energy in the form of photon, okay? And this energy is of the amount which is equals to h mu, which is hc by lambda. That means the amount of energy that it is going to absorb will be determined by the wavelength that it is getting. Okay, so if it is getting a larger wavelength, that means it is going to get smaller amount of energy. If it is getting a longer smaller wavelength, then that means it will get a larger energy. What is the meaning? That means that if it is getting a light of radio wave frequency, then it will get a smaller amount of energy. If it is getting a light of a photon of a gamma ray frequency, then it will get more amount of energy. Okay, whatever it is, it gets some energy, it becomes excited. Now it is so excited that it is unstable. Okay, this is unstable over here. Unstable. Now, as it is unstable, it will try to come back to its normal ground state. So it will. So while coming to the normal ground state, what it is doing is that it is It is emitting the energy. So it is emission of photon. So basically, when you are doing spectroscopy, you are studying about the absorption and emission properties of various molecules, various electrons, various functional groups. So these absorption and emission properties are different, and that determines the kind of spectroscopic techniques that can be utilized. That means that radio waves will have, since waves have the least energy, so this amount of energy cannot be sufficient to just knock off an electron from its shell outside the atom. Okay, so radio waves will not provide that much of energy, but UV range will provide that much of energy. No, gamma rays can provide that much of energy, that electron will just completely get out from the atom. But UV rays will provide that much of energy that electrons can move from a lower energy state to a higher energy state. So now we'll see that one by one, that how much energy each wave has, and that energy is equivalent to study which property of of the product. Okay, so when you are studying about a particular atomic or a molecular process, okay, so basically when you are going for spectrometric technique, you are actually studying about the various atomic processes or the molecular processes that happens within an atom or a molecule, whatever your context is. Okay, so in that context, you can see that for a molecule or for an electron, let's consider over here an electron, you can study the electronic transitions. That means it is going from lower energy orbit to a higher energy orbit. Electrons moves in Electrons moves in orbitals, but now for the convenience point of view, convenience per se, we'll say that they moves in orbit, but they move in orbitals in 3D space that we have all studied. Fine. So you can study that it can move from one energy state to another energy state, that is from one orbit to another orbit, that is electronic transitions. Then the rotation of the electrons, then the vibration of the electrons, and then the transitions that happens. There are some electronic transitions and there are some nuclear transitions that also happens. Okay, so these four properties we can study and we can evaluate with the help of spectroscopic techniques. And not only that, we can study these properties. Important thing to understand is that you cannot study all of the properties through just one set of rays, because for vibration you need different amount of energy, for rotation you need different amount of energy, for transitions you need different amount of energy. The energy which is required for studying the vibrational properties of a molecule of an electron or of the rotational property of an electron is not sufficient to study about the electronic transitions of an electron. For electronic transitions, you need greater amount of energy. But for studying rotation or vibration, you will require lesser amount of energy. So this is important to understand that the amount of energy that an electron will emit in rotating or vibrating or electronic transition is different, and that energy corresponds to some particular types of waves. For example, so the amount of energy that an electron absorbs and emit, it corresponds to the UV visible region. For rotation vibration, it corresponds to radio waves or microwaves regions. Okay, so like this we'll just see. Okay, so first is your radio waves. So radio waves have very low energies, and that correspond to the energy differences that in the nuclear and electron states. That means your nucleus is also spinning and your electron is also spinning. Okay, both your nucleus and your electron both are spinning. So when a nucleus spins, you can see over here, this is your nucleus. Okay, just a minute. Yes, see, this is your nucleus. So your nucleus is spinning. So it can spin either in a clockwise direction, or it can spin in an anti-clockwise direction. Similarly, your electron, it can also spin in an, just like the earth, it rotates and revolves both. They, in a similar manner, your nucleus also spins, your electron also spin and also rotates within the in the circumference. So the energy that it is taking for the spin, it corresponds to radio waves. Okay, so these frequencies corresponds to radio waves, and therefore they are used for studying uh, the properties of a nucleus or electron with the help of two spectroscopic techniques: nuclear magnetic resonance and electron paramagnetic resonance spectroscopy, that is NMR or EPR. So for NMR spectroscopy, which waves corresponds? Radio waves. For EPR, that is electron paramagnetic resonance spectroscopy, which waves corresponds? Radio waves. Okay, so radio waves are responsible for NMR and EPR spectroscopy. Is it clear? Okay. Then we come to microwaves. You can see over here, microwaves have energy a little between that of radio waves. So you can see microwaves have energy between radio waves and infrared waves. So again, you can also use microwaves for studying the electronic properties. And so see, for studying the for NMR, only radio waves are used. Okay, but that means for studying the properties of a nucleus, NMR is nuclear magnetic resonance. For NMR, only radio waves are there. That means for studying the property of a nucleus, only radio waves are used. But for studying the properties of an electron, you can use either radio waves or microwaves. So, microwaves has applications in rotational spectroscopy and again in EPR. Now we come to infrared radiation. So infrared has a little more. Now this is used to study the vibrational properties. What is the meaning of vibrational properties? So as we are seeing, what an electron can do. Electron can rotate. Okay, electron can spin. It can spin either in clockwise direction or in anti-clockwise direction. And doing so, the frequency with that corresponds to is of microwaves or radio waves. Now, electron can also vibrate. Okay, or a molecule can have vibrations. So for that, you need energy that corresponds to infrared radiation. That means during vibration, the frequency which corresponds of the electromagnetic spectrum is of infrared region. So then it is known as vibrational spectroscopy, which is used for the study of functional groups. So functional group identification can be done with the help of infrared radiations, with the help of vibrational spectroscopy. So whenever it comes about vibrational spectroscopy, you have to remember infrared radiations. Fine. Then comes again important one that we have to study a little bit in detail, and that is your UV visible region. So you can see that this electron is going from a lower energy state to a higher energy state. Okay, so here it has more energy. So electron, it can spin. plus 1 by 2 minus 1 by 2. It can vibrate and it can have transitions. So electronic transitions, that means moving from one state to another state, one ground state to excited state, or then again coming from excited to ground, it depends. So for that, the energy that corresponds is that comes under ultraviolet, sorry, UV visible region. Okay, then we come to the x-rays. So what x-rays corresponds to, it causes transition in the internal electrons of the molecules. So basically x-rays causes the internal transition of the molecules. Then okay, so up till now we have studied about all the kind of transitions that happens. Now we'll see a little bit in detail about UV visible spectroscopy. So what they are saying, that you can see over here that there are different kind of transition that happens: sigma, sigma star, pi, pi star. So I'm not going to be into very much detail about it, because you have already studied in your school level. Just you can just go through it and read like what all is there. Now we come to the spectrophotometer. Now spectrophotometer can be either a single beam spectrophotometer or a double beam spectrophotometer. So what is a single beam spectrophotometer is that okay, just give me 1 minute to change the setting. Okay. Fine. So, what is the meaning of a single beam spectrophotometer? Single beam spectrophotometer means that uh, so this is your light source. Okay, this is your light source. Light source can be either a UV light source or a visible light source. Then it falls on a monochromator. What is the meaning of monochromator? Monochromator means mono means chroma means color. Okay, so that means from when you are getting light, the light is going into all directions, but you want light of a single direction, so it will just cut out all the other lights and just light in one direction will move from this monochromator. And then you have a reference cell, and then there is a detector. So basically what happens, the light enters the instrument through an entrance slit, okay, is collimated and focused onto the dispersing element, okay. The light of desired wavelength is selected simply by rotating the monochromator. Obviously, that means that you need, when you are getting a UV light source, the light is coming and this light is of different wavelengths, many wavelengths, but you want light of a single wavelength. Okay, so you, to get a light of a single wavelength, you have to use a monochromator. So monochromator cuts off the light of all other wavelengths except the wavelength that you want. Then there is a reference cell. Okay, this is a single beam spectrophotometer. Now what is a double beam spectrophotometer? You can see that everything is same, just you have a reference cell and sample cell both. So what does it means, it that a double beam has two light beams, and one of which passes through a reference cell and one of which passes through the sample cell. So therefore there are no fluctuations. So what happens is that whenever you are using spectrophotometry, okay, spectroscopy, whenever you are doing, so you have to make sure that first you are, so okay, so whenever you are doing any experiment, okay, whether it's about spectroscopy, it's about any molecular bios experiment, or any protein level, also any kind of experiment you are doing, you have to normalize your result. What is the meaning of that? That you have to reduce or negate all the false positive signals. You have to reduce the noise. Just like when you're doing antigen antibody interactions, you're using immunohistochemistry, cytochemistry, or fluorescence, you do blocking to reduce the background signals. When you're doing real time also, then you have uh, gap DH, which reduce the background signals. Similarly, what you have to do is that your protein, it is mixed in some solution, it is mixed in some liquid, okay. That liquid can also give you some reading, but that is not the correct reading, that is a false positive reading. So you put that liquid in which your protein is dissolved as a reference, and then you take your reading and you subtract the reading that you got from your reference to with your sample, so that whatever result you are getting in the detector, that is solely because of your protein and not because of the solution in which the protein is mixed. So what happens in your single beam spectroscopy, that you have a reference cell which corresponds to the liquid in which the protein is dissolved, and sample cell actually has the sample with along with the liquid. So first you have to put your reference tube, then you take a reading, then you have to remove the reference tube, and then you have to put your sample tube. So one by one you have to do, and it might not produce very reproducible results. Okay, it may have some I mean there can be fluctuations of the light source or the instrument, because one time you are doing it can give some reading, and another time when you did put your sample for your sample, it might have some fluctuation, so the results will not be so reproducible. So what if at a time you are measuring your reference cell also, sample also, and your sample, I mean your sample cell also. So for that you have now double beam spectrophotometers in which you can detect the values that are coming from reference cell and sample cell at a time simultaneously, you can detect. So that is the difference between your single beam spectrophotometers and double beam spectrophotometer. Now, UV visible spectroscopy basically follows a law. That means, okay, so spectrophotometer will give us some reading, and that reading is actually telling us the concentration, absorbance. That means, um, reference cell, that means the liquid in which your protein is dissolved, that liquid suppose is giving you an absorbance value of 5. Okay, this is nowhere to the real values, I'm just giving you a simple examples. Then you are getting a value of, let's say, 15 in your sample cell. So your actual absorbance is 15 minus 5, which is 10, because this is the background, it has to be removed. So actual absorbance that you have got is 10. So that means from the spectroscopy what you are getting is the absorbance. But how this absorbance can be related to the concentration, because we want, our objective is to find how much sample is present, what is the concentration of the sample, we are not concerned about the absorbance. So then this Beer-Lambert law came into picture, and it told us that absorbance is directly proportional to concentration. That means if your sample is very concentrated with your product of interest, it will give a good absorbance rating. If your sample is less concentrated with your protein of interest or your product of interest, it will give you low absorbance. Okay, so this is your Beer-Lambert's law, which says absorbance is directly proportional to concentration. And when you are removing the so this goes like, absorbance is directly proportional to concentration. You are removing that proportional sign, you are putting the constant, that is epsilon and c, sorry, epsilon and L. Epsilon is the molar coefficient and L is basically the distance which is measured in centimeters. Okay, this is your Beard's Lambert law. I think I am explaining you all the points in a very great detail so that you don't have any problem. And even if you have missed one or two points while you were, you know, reading, I mean, going through the search recorded lecture, at least it will help you out. Okay. Then, so absorbance is equals to epsilon Cl. Then UV visible spectroscopy is basically based on Beer-Lambert law. Okay. But this the Beer-Lambert law that you study has some exceptions. Okay. And that exceptions are the points where this Beer-Lambert law cannot be followed. When your sample is of very high concentration. So basically Beer-Lambert law holds good only for dilute solutions. Why? Because at higher concentrations, the molecule comes in so close proximity that they start influencing each other. That means they are so close to each other that one molecule start affecting the electronic properties of the adjacent molecules. And therefore, in that case, your Beer-Lambert law does not hold true. So, therefore, Beer-Lambert law is not very good when the sample is of very high concentration. Then second is your chemical reactions. What is the meaning of chemical reactions? If a molecule undergoes a chemical reaction and then the spectroscopic properties of the reacted and unreacted molecules will be different. That means if these are some molecules, okay, same molecules, but these molecules are going some chemical reactions and these molecules are not going chemical reactions, so then the properties of these will be different. Therefore, the spectroscopic properties will also be different and Beer-Lambert law cannot hold the place. Then comes your instrumental factor. That Beer-Lambert law is good only for monochromatic light. Polychromatic light, if you are using, then there would be a deviation. Okay. Now, there are certain terms. I'll just give you 1 minute. You can just go through these terms and then we'll one by one we'll try to understand. Just go through what is isochromic, hyperchromic. 1 minute, just read it out. Okay. So what you could understand from this is basically the kind of shifts. First is bathochromic shift, which is when the spectrum shift towards a longer wavelength. This side is bathochromic shift. Hypsochromic shift when it shifts towards a smaller wavelength. Hyperchromic shifted when there is an increase in the absorption intensity, and hypochromic shift is when there is a decrease in the absorption intensity. So these are, these are the terms which are very important for you to learn. Try to memorize them. Okay. Now, now we'll solve the questions because we have one more lecture to finish. Just a minute. The units of absorbance and transmittance is, sorry, are AU, micron, micrometer, dimensions. What is the unit? What is the meaning of AU? Think. Those who are watching on YouTube also think. What is the unit of AU? What is the meaning of AU? AU means arbitrary unit. That means there is no unit of absorbance and transmission because both the numerator and denominator units gets cancelled up. Therefore, there is no unit. We just give it an arbitrary unit which is AU. The shift of absorbance spectra towards shorter and longer wavelength is. Just now we have studied. What is it? A is hyperchromic and hypochromic shift respectively. Hypsochromic and bathochromic shift respectively. Bathochromic and hypsochromic shift respectively. Or hypochromic and hyperchromic shift. What is the answer of seventh question? Think. What should be the answer? Okay, the answer is B. Okay, this is the answer. That means shift of absorbance spectra towards shorter and longer wavelength is known as hypsochromic shift and bathochromic shift respectively. Then lowest and highest energy rays are, which has lowest energy rays and highest energy rays? Eighth question. Lowest energy is radio waves and highest energy is gamma rays. Next question is, the absorption pattern of molecules depends on the type of neighborhood atom. The absorption and emission patterns of molecules can be studied by. We have to study about the absorption and emission patterns. It can be studied by which has the highest energy here. Tell me. Which has the highest energy? Gamma rays has the highest energy. Then lowest energy, microwaves. Then infrared rays, then UV, then gamma rays. This is the energy this thing. Now, for studying the absorption and emission pattern, so absorption and emission pattern will come only when an electron will move from its lower energy state to a higher energy state. When it is moving from a lower energy to a higher energy, it is doing some kind of absorption of photons. When it is returning from higher energy to lower energy state, it is emitting that photon. So then only you will have absorption and emission patterns. So you have to understand like this, that absorption and emission patterns, it will come when a molecule will move from a lower to a higher energy state and then again comes back to from the higher to the lower energy state. And this is possible only when they corresponds to UV visible radiations. So the answer for the ninth question is UV visible radiations. Next, rotation of protons and electrons can be studied by. We have just in this chapter we have studied this a little bit in detail also. I'll give you 1 minute. Think of the answer. Think what should be the answer to this question. For protons, we can only use NMR. For electrons, we can use NMR and EPR both. Okay, because NMR corresponds to what? Radio waves. EPR, radio and micro both. So the answer is A. NMR and EPR respectively. Functional group identification can be studied by A. Microwaves, B. Radio waves, C. Infrared radiations, or D. Gamma rays. 11th. What is the answer? Think. So, functional group identification can be studied with the help of infrared radiations. We have studied. Okay. Now we'll come to the last, the next last lecture. I think this is the last lecture, which is spectroscopy part 2. Here we will study about the UV spectroscopy. We have a little bit studied about the UV spectroscopy already. Then we'll study about the infrared spectroscopy, then degree of freedom and molecular vibrations, and then infrared spectra. So these are these questions I think we have already done. I think they are repeated absorbance and okay. So need not to go for these questions. Fine. Just a minute. Key. Okay, so now we'll come to this thing. So, spectroscopy is about absorption and emission, but it is not just absorption and emission, it is much more than that. We will study later. So, now we are seeing the applications of hmm, applications of UV visible spectroscopy. Okay. So, these are the applications. They can be used for, they have an influence on the functional groups, conjugated double bond and conjugated double bond and absorption peaks, large molecular wavelength, and all this. Then we come to infrared spectroscopy. This is the infrared region. Okay, this is your X-rays, UV visible range. This is the radio waves and microwaves. So infrared is somewhere between the visible range and microwaves. Now infrared waves are also subdivided into three kinds of different waves. First is your near infrared rays, second is your middle infrared rays, and third is your far infrared rays. Okay, so basically, infrared spectroscopy is used to study the vibrational properties of a molecule. And these vibrational properties of a molecules are like a fingerprint. So these vibration molecules are used to study about the functional groups of the molecule. Important. Okay. So here what is written? That infrared radiation, infrared region of the electromagnetic spectrum, it lies between the visible and the microwave, and therefore it spans the wavelength of 0.78 to 250 micrometer. Okay. And the energies associated with the molecular vibrations are smaller than that of electronic transition. Obviously, see, that's what I was talking about. That to study different properties of molecule, different energies are associated. That means the energy which is required for the absorption and emission of an electron is different from the energy that is required for vibration of an electron. So for an electron to vibrate, it will need lesser amount of energy, and that energy corresponds to the infrared radiations. Whereas for an electron to just spin, it will need even lesser energy, that corresponds to microwave or radio wave frequency. So for example, if I have to just go from one room to another room, I would need more amount of energy. Or if I just have to turn around my own place, I would need less amount of energy. But if I have to go from my floor, suppose if I'm on a second floor to 12th floor, then I would need more amount of energy, isn't it? Just for me to turn at my own place would require lesser amount of energy than for me to go from the first floor to, let's say, 10th floor. So same thing happens with the likewise you can correlate with the molecule with an electron also, that for an electron to spin, it will need least amount of energy. For an electron to vibrate, it will need a little more amount of energy. For an electron to go from a lower energy state to higher energy state and come back to that lower energy state, it will need a little more amount of energy. For an electron to just completely get out of the atom, it will need the most amount of energy. So for the electrons to vibrate, the energy that it is needed, it corresponds to infrared radiations. Therefore, infrared spectroscopy is used to probe the vibrations in molecules, and therefore it is also known as vibrational spectroscopy. Okay, now we know that okay, infrared radiations corresponds to vibrational spectroscopy, but not, see, infrared ray this infrared radiations are also divided into three parts: near infrared, middle infrared, and far infrared. So basically it is the middle infrared region which is required for the studying of molecular vibrations. That means not all the range of infrared radiations are responsible for studying the molecular vibrations. The near infrared radiations are responsible for the study of the molecular vibrations. So basically, vibrational spectroscopy, when we're talking about, we are actually studying about the what? What we are studying actually? Middle infrared radiations we are studying. Is it fine? Okay, just a minute. There is some network problem, it seems. Just wait for a minute. Yeah, fine. Mhm. Then there comes the degree of freedom and molecular vibration. You can just go through it. Now we'll just see the basic things, and then we'll come to the question parts. And then if anybody has any questions, then we can solve those questions. Otherwise, we'll just end up this thing. Okay, so basically, you have to understand. Okay, when we'll solve the questions at that time only, I will make you understand. But you should keep in your mind that they for infrared spectroscopy, the molecule should be infrared active. Okay, so infrared active means that when it absorbs the infrared radiation, it results in some kinds of vibrations. Okay, this we have studied. Now, those vibrations should result in change in dipole moment. Okay, so what we are saying is that when we are talking about infrared spectroscopy, so infrared spectroscopy will cause some kinds of vibrations, and those vibrations should result in change in the dipole moment when we are talking about molecules. So basically, if you have a diatomic molecule means a molecule which has two atoms that has one mode of vibration may not absorb an infrared radiation if the vibration does not accompany a change in the dipole moment. Okay, if there is no change in dipole moment, then the molecule will not be infrared active. So, for homonuclear diatomic molecules, for example, H2N2O2, there is no change in the dipole moment. Whereas molecules such as carbon monoxide, it has a change in the dipole moment, therefore it is infrared active. So what we got to know about here that not all the molecules are infrared active. Okay, so only those molecules which have a change in the dipole movement, they are only infrared active. Only those molecules that have a change in the dipole moment. Now, what is the meaning of change in the dipole moment? Let's talk about this in a little more detail. Okay. Homoatomic, homonuclear diatomic molecules. Hydrogen, nitrogen, oxygen. And then carbon monoxide. These two examples we will take. Okay. So, we have H2 and we have CO. Both are same. So, attraction and repulsion of the electrons between the two atoms would be same because they both are same. Here, oxygen has a partial negative charge, carbon will have a partial positive charge. So there would be two poles now, like a negative pole and a positive pole. So there is the establishment of dipole, therefore there is an establishment of dipole movement. So, and this partial negative and partial positive that I'm saying, so how it depends, how could I say that oxygen has a partial negative charge and carbon has a partial positive charge? Think, how is it possible? Okay. So see whether it will have a partial negative charge or it will have a partial positive charge. It depends on the number of electrons that it has in the valence cell. So the valency will determine that it will be a partial negative or partial positive. Okay, so if it has more electrons and it can donate some electrons, or it needs some electrons, if it can donate some electrons, and so that it can become partially positive or neutral, or it is positive means it needs more electrons. So likewise you have to understand. Fine. Okay, valency is important. If I'm not going to explain the complete this thing, how valency happens, how valency is calculated, what is the meaning of valency, I'm assuming that you all have studied about valency in your school, so you know what valency is. Fine. Okay, so this was about this thing, your infrared spectroscopy basics. So one thing about infrared spectroscopy is that infrared spectroscopy is applicable only when your molecule is infrared active. And for a molecule to be infrared active, it should have a change in the dipole movement. And change in the dipole movement is not possible for homonuclear diatomic molecule such as hydrogen, nitrogen, oxygen. Whereas when there is a vibration in a molecule such as heteronuclear molecules such as carbon monoxide, then there is a change in the dipole movement, and therefore there is infrared activity. Why? Because vibration of bond involving two atoms that have large electronegativity difference. So this is important while we were discussing about the carbon monoxide example. So in CO, this is your partially negative and this is your partially positive. So what is there? There is electronegativity difference. Okay. And because of this electronegativity difference, there is a change in the dipole moment, and therefore this molecule is infrared active. Is it clear to everybody? So we are studying about spectroscopy. Okay. So in spectroscopy, what are we studying? We are studying that different kinds of spectroscopy techniques are based on the different wavelengths of of your electromagnetic spectrum. And why different wavelengths are considered? Because for a single electron can have different kinds of properties. Electrons can either spin, electrons can either vibrate, electrons can either go from a lower energy shell to a high energy shell. Each and every action requires different amount of energy. Okay, likewise, just like in our case, like we do small actions. Suppose for me to lift a pen and to lift a 5 kg weight, so lifting a pen would need just a very less amount of energy, whereas lifting a weight would need a very greater amount of energy. So likewise for electron also, for molecules also, different, for doing different modes of action, different amount of energies are needed, and those different amount of energy corresponds to different wavelengths of electromagnetic spectrum. Always remember, different amount of energies which are needed for an electron to perform different kinds of function corresponds to different electromagnetic spectrum. That is why in the beginning I have studied, I have made you revise the energy association of different electromagnetic ranges. That how, what is the energy of gamma rays, what is the energy of radio waves, and how the relationship between energy and waves depends. So energy is inversely proportional to wavelength. That means if the wavelength is more, energy would be less. But energy is directly proportional to frequency. That means if the frequency is more, energy would also be more. If frequency is less, energy would also be less. So right now we were studying about the infrared spectroscopy, and then we'll see what are the applications of infrared spectroscopy. Okay. So the first application of infrared spectroscopy is the identification of functional groups. Okay. So just a minute. Okay. How you can determine the functional group? Because first of all, if there is a change in the dipole moment or not, if there is no change in the dipole moment, that means functional group is a homonuclear diatomic molecule. So likewise, in various ways you can reduce and you can just get to know that whether there is a change in the functional group or not, and therefore, sorry, change in the dipole moment or not, and therefore you can determine the functional groups. Then identification of compounds. What is the meaning of identification of compounds? So the fingerprint region of infrared spectrum is unique to each compound. It is possible to identify a compound from its infrared spectrum if the spectrum for the compound is already known and available for comparison. Okay, so this is particularly useful in pharmaceutical research and development. A patented drug, if suspected to be synthesized by another pharmaceutical company, can easily be identified by comparing the infrared spectra in the fingerprint region. That means that what you have to do for the identification of compounds. So each compound will have a unique infrared spectra. So that infrared spectra would be different for each and every compound. That is what is important. So that is why how you can differentiate between the two. Suppose I made a new drug, okay, and in my new drug there is something which is very unique, and there is one another company which has also made, which is my competitor, it has also made a drug, and it is also working very well just like my drug is working. So now I am suspecting that they are using my unique component. Okay, suppose I made a drug A, and in drug A I have used a drug, I have made, just a minute, I don't know what happens sometimes to the computer, sorry. Yeah, so we are talking about the applications. First is identification of the functional group. Second is, what is second? Identification of compounds. Identification compounds. So how it is possible? I made a drug name A. I have cloned and I have gotten to know that there is a unique compound. I named it as small x, which is important to treat diabetes, suppose. Okay, which is important to treat diabetes. And I have, this is my drug name, commercial name A, and this compound I have incorporated in my drug. Another competing company made another compound and they gave it a name as A star, which is better than my compound. And this is also behaving in a very similar manner, and this is also curing diabetes just like my compound is doing. So now I am suspecting that this company has somewhat, they are using my patented compound that they're not authorized to use. My patented discovered this thing. So what I will do is, when I will do the infrared spectroscopy, I will try to observe the infrared spectrum of each and every constituent of this particular drug. And what I got to know that one infrared spectrum, it corresponds to the infrared spectrum of my unique X component. So that means they are using my compound. They are using my component X. So what does it mean? That the infrared spectrum is unique to each and every component. And therefore it becomes a very important criteria. It acts like a fingerprint. Okay? This is one important thing. See, this is what they are written, that a patented drug, if suspected to be synthesized by another pharmaceutical company, can easily be identified by comparing the infrared spectrum in the fingerprint region. So, identification of compound becomes another application. Then, another application is presence of impurities. What does it mean? Comparison of the infrared spectra of the given compound with the spectra of a pure compound helps in the assessment of its purity. If the It is important to ascertain the purity of active molecules and the excipients used in preparing drug formulations. Basically, if you have a compound and you have a standard compound as in which is available in the market, which is pure, and you are also making something like that. So if this is your standard compound, which you know is 100% pure, this is your made compound. So now you have the infrared spectrum of this standard compound. The infrared spectrum should match exactly with it. If there are some other infrared spectra in this made compound, those are your impurities. If you have three infrared spectrum, you are getting five infrared spectrum. That means two spectrums are because of impurities which are not present over here. Okay, so therefore you can determine the purity. So third thing that we can do with the help of infrared spectroscopy is determination of the purity of the compound. And how you can determine? By comparing the infrared spectrum. Is it clear? Okay, just a minute. Okay. Next, what is the application? It happens like this. See, there are so many applications that are associated. Structural transitions. Just a minute. Like structural transitions in lipids, then protein and peptide structure. So you can determine the protein and peptide structure also with the help of infrared spectroscopy. You can determine the functional groups which are present. So basically, these are all the applications. So if you just kind of if you try to summarize of what we have studied in this particular week 10 module is that after your right from the beginning, let's see what we have studied. First, we have tried to clone a particular gene. Okay, so we have first identified that gene from the whole genome, we have extracted that gene, we have amplified that gene. Now we have that gene. Then we decided what kind of vector we should use for the cloning of that gene. Okay, so for the decision of the vector, we have to keep in mind whether we need a cloning vector or an expression vector. Here, because we wanted to get the product, therefore we had a expression vector. We decided that okay, this expression vector, puck series vector or pet series vector, we will use. Now, because it's an expression vector, so apart from the origin of replication, selectable marker gene, and multiple cloning site, it need to have certain more features such as ribosome binding site, transcription, translation start site, and end sites also. Okay, so now we have selected our vector. now we have to clone our gene of interest into that vector. So for that, what we have done, we have digested our insert and vector with the same restriction enzyme. Okay, I have decided digested my insert and vector with the same restriction enzyme. Then what I did, I ligated them. Then after ligation, I did the transformation. Then after transformation, I screened them. Then after screening, I know that okay, now my gene of interest is present and it is expressing also. Now I want to extract my product or and then purify my product. After the expression of, here the product is protein. Okay, we're talking about protein. So first thing is to express your protein, and after expressing your protein you have to extract the protein and purify the protein. For the extraction of protein, what we have to do, we have to first lyse our cell. For the lysis of the cell, we can use certain detergents or certain enzymes and other reagents that will just cut open the cell wall and cut open the cell membrane, and all the components are released. Okay, so for the lysing of the cell, you have lysed it, and all the components which were present in the proteins are released. So along with your protein that you have cloned and expressed, there must be some hundreds and thousands of proteins more which are present. So from that you have to purify your protein of interest. So for the purification of protein of interest, now see, after up till expression, what we are doing, up till expression is upstream processing. After the expression, the extraction, the purification, the characterization, it all comes under your downstream processing. So now that I have I have of of my this thing product of my cell, I want to purify my protein. So for the purification of protein, I will use various kind of chromatographic techniques. So depending upon what kind of what are the properties of my protein, I will exploit the type of chromatography technique that I can use. If my protein is charged, then I can use your anion exchange chromatography. If it is hydrophobic, then I can use hydrophobic interaction chromatography. If it has certain affinity to certain ligand, I can use affinity chromatography. If it is a globular protein, it has a very different mass and size compared to other proteins which are present in the same cell. I can use gel filtration chromatography. So now after depending upon my properties, I selected one chromatographic technique, and then I have isolated my protein also, purified my protein also. Now I have my protein with me, purified protein with me. Up till here, you have studied till in week 9. So in week 10, what we have studied, that after the extraction and purification of the protein, now we want to characterize it. That means we want to know its properties. Okay, so characterization of protein means that we want to know about its properties. What are the properties of the proteins? And what all properties we can study or which are important? That what is the molecular weight of the protein? Okay, what is the sequence? If we know the sequence will solve most of the problems. Okay, so if you know the sequence of the protein, then your 90% of job is done. So sequencing is very important. So molecular weight of the protein, then sequence of the protein, then what are the functional groups that are present, determines the property and it determines the kind of work that a protein will do. So understanding of the functional group is very important. Okay. So for this, we I'm, I think my computer just got hang. No, it's not working. Sorry, it got hanged. Yeah. For the determination of functional group, we studied about the various spectroscopic techniques that can be applied. So these spectroscopic techniques, they depend upon the type of wavelength. So I am not we talked about that if an electron is present, if an electron is spinning, or whether the electron is moving from a lower energy level to a higher energy level, or the electron is vibrating. So different for performing different works, different energy waves are required, and that electron will use. So in that context, we have studied about different kinds of spectroscopy, right, starting from radio waves to microwaves, infrared waves, then UV-visible rays, then gamma rays, X-rays. We have studied about all of them. So we have revised what was there in this chapter, the whole lecture 1, 2, and 3. So now I'll just quickly try to we'll just quickly try to solve the questions. Okay. Okay. The first question is, I mean, first question of this is, in spectrophotometric cell of 2 centimeter path length, the solution of substance show absorbance value of 1. If molar absorptivity of compound is 2 into 10 to the power 4, calcul calculate the concentration of substance in solution. How we can do this? So we can do this with the help of Beard's-Lambert law, which states absorbance is directly proportional to concentration, which means absorbance is equals to epsilon Cl. So concentration is equals to absorbance upon epsilon L. Absorbance upon epsilon L. Absorbance is given as 1. Epsilon value is given as 2 into 10 to the power 4. Path length is given as 2 centimeter. Can it be calculated now? It is easy to calculate. After calculation, the answer comes this. First one. Next question is, homomolecular molecules are infrared active. Inactive because they cannot vibrate. They have only stretching vibrations. They have no bending vibrations. The dipole moment does not change during vibrations. So why homomolecular molecules means homonuclear. It should be homonuclear molecules, diatomic molecules. Di So they do vibrate, but their vibration leads to no change in the dipole moment. Therefore, the answer is D. That means vibrations does not cause any change in the dipole moment. So these homomolecular molecules or homonuclear diatomic molecules, they do vibrate, but there is no change in the dipole moment. Therefore, they are not infrared active. They are infrared inactive. Next question. Infrared spectroscopy is used to identify dash in organic molecules. A. Functional group. B. Geometry. C. Number of neutrons. D. Number of protons. We have studied this. 1 minute to think. Okay. So, infrared spectroscopy is used to identify the functional groups in organic compounds. Then, the bandwidth in infrared dash due to hydrogen bonding. So, what happens to the bandwidth? It increases due to hydrogen bonding. Next question is, the region of electromagnetic spectrum mostly used for infrared spectroscopy is near IR, mid IR, far IR, or very far IR. So, what should be the answer for this question? So, we just see quickly. Uh, Here we have studied about that. So, this infrared region is actually divided into near infrared, middle infrared, and far infrared. But amongst the three, it is the near infrared region, sorry, mid infrared region, which is the region of interest for studying the molecular vibrations. Okay, this mid infrared region corresponds to the wavelength of 2.5 to 25 micrometer, and it has a frequency of 4000 to 400 centimeters, minus 1. So the answer of this question would be mid infrared region. Then the relationship between absorption and transmission is A. Absorption is logarithmic of transmittance. B. Absorption is reciprocal of transmittance. C. Absorption is negative logarithm of transmittance. Yeah, D. Absorption is multiple of transmittance. So what should be the answer? See, absorbance is, I'll give one clue is that absorbance is always reciprocal of, I mean, not reciprocal. Absorbance and transmittance do not have a direct relationship. Okay. Now, what should be the answer? So the answer would be absorption is negative logarithm of transmittance. Next question. Two compounds A and B have molar absorptivity of 1200 and 1500 molar, the unit respectively. The correct statement regarding this is compound A can be detected at very low concentration than compound B. Compound B can be detected at very low concentration than compound A. Both compounds can be detected at very dilute concentration, and molar absorptivity have no influence or detection of compounds. So let's try to see this question. A has an absorptivity of 1200. Okay. B has an absorptivity of 1500. So, which has a higher absorptivity? B. That means this can be detected at even low concentration in comparison to compound because it has a higher molar absorptivity. Therefore, it can be detected at lower concentration than compound A. So, what would be the correct answer then? The correct answer would be B. That means compound can be detected at very low concentration. Compound B can be detected at very low concentration than compound A. Okay. Next question is question 23. I think this is the last question. Just a minute. Is this? Yes, this is the last question for the day. Okay. The heights of the peaks in mass spectrum represents what? Number of isotopes, average atomic mass, charge to mass ratio, or relative abundance of each isotopes. 1 minute to think. Think. So, just we'll go through here. Mm, you have to go through these applications actually. So I have tried to cover the applications as much as I could, as much within the time frame that we have. But you have to understand that these applications are very important, okay? Because these applications, not just for the information per se, but these applications are important because these will give you the basic information, and these are actually the applicatory based questions which comes in your gate and some other competitive examinations. So it is important. So first we'll just solve this question, the last question, and then we'll just quickly revise this. I think we haven't revised this one. I just saw. So we'll just revise it. Yeah. So the height of the peak in mass spectrum, it represents the D. Option is correct answer is option D. That is relative abundance of each isotopes. Okay, I'll just explain you. This is the correct answer. Answer D. So just see here. See how infrared spectroscopy can be used to study the functional groups. We just said that infrared spectroscopy is used to study the functional groups because different functional groups will give us different infrared spectrum. See, this is your benzene. This black one is benzene. If you add one functional group to, that is OH, it becomes phenol. The spectra changes. Then you add another nitrogen here, it becomes paranitrophenol. Again, the spectra changes. So, can you see the influence of functional groups? The core structure, benzene, the core structure is the same only. Here also the core structure is same. Here also the core structure is same. Here also the core structure is same. The core structure is same in all the three structures. But the functional groups are different. Here there is no functional group. Here there is functional group OH. Here there is OH and nitrogen attached to at the B position. So this is just phenol, this is paranitrophenol. And the difference of these functional groups are changing the infrared spectrum. So any change in the infrared spectrum, so basically we have standards like that OH will give this kind of a spectrum. Nitrophenol, paranitrophenol, I mean this nitrogen at the P position will give this kind of spectrum. So because we have a known set of spectrums, a known set of standard peaks as reference already with us, So whatever peaks we are getting for our product, for our protein of interest, for our sample, we can compare that with the peaks which are available, which are standards. And then we can get to know that what all functional groups are present in our particular protein. And by the determination of functional group, we can determine the properties. Okay. So whether if there are some amino acids, if there are functional groups like phenol and benzene, then it will have different kinds of properties. So basically the properties of what we are trying to do is we are trying to characterize a protein, right? We want to study about the properties of the proteins, how the protein will behave, how the protein will react in situations, I mean environmental conditions, at different pH and pH concentration and different solubility, etc. So that is helpful with the help of the information of the functional group, and those functional groups you can study with the help of peaks. Again, you see here, just a minute. Again, you see here, here you have studied about the effect of different functional groups on the peak. Okay, effect of different functional groups on the peak. Now we'll see the influence of, I'm sorry, I don't know why this happens every time, it's really irritating. Yeah, then the effect of double bonds or conjugated double bond. You can see this is benzene, 2 naphthalene, different peak. 3 are there, anthracene, peak is different. You can see how the double bond system and conjugated bond system is changing the peaks, the absorbance peak. That means it needs more energy. Anthracene needs more energy than benzene, because it's, see, benzene is giving your absorbance somewhere here, but anthracene is giving somewhere here. It requires more energy than benzene. So like this. Then next is, you see here, large molecular framework and small conjugated system. This is a small conjugated system, this is a large molecule framework. Okay, so you can see that a small conjugated system will lead lesser, will have a different peak than a large conjugated system. You can see this is benzene and this is prednisone, so zolone. So here also the peaks are different. So you can see here that different uh, functional groups or different double bond systems or different conjugated systems has different effects on the peaks. If your conjugated systems is very complex, if your conjugated system is simple, if you have simple structure which has a lot of resonance double bonds, structure which has a lot of functional groups, everything will give you different peaks. So basically it becomes unique property. So you have to understand that OH group has a specific peak. Okay, now whatever specific peak OH group has, that particular peak is a characteristic for OH. So doesn't matter at which kind of a uh, basic structure, like what is the core structure at which OH is present, whether it is present in a after carbonyl group, whether it is present in a benzene, wherever OH is present, OH will give you the same structure in any base, like in any base framework it is present. The base framework can be different, but functional group will, the structure of the functional groups, I mean the peaks, the infrared spectrum of the functional group will not differ on the basis of their base structure to which they are attached. So, because this is a property which is very unique for the functional groups, therefore you can identify functional groups. Otherwise, you could not identify functional groups. Suppose if when an OH is present in benzene and when a OH is present in a very long carbon chain, after a very long carbon chain, if I say that will the OH which is present with a benzene will have a same peak with the OH which is present after a very long carbon chain, what would be your answer? Think, what should be the answer? OH group, when it is present in a benzene, I mean in phenol, and OH, which is present in a very long carbon chain. The infrared peak of both the OH would be same or different, and why? And what are its consequences? Can you think of any reasonable explanation for it? What should be a reasonable explanation for this? 1 minute to think. So basically, you have to understand that the infrared peak of OH would be same irrespective of the base structure it is attached to. That is what I said. So whether it is attached to a benzene or whether it is attached to a long carbon chain, the infrared peak would be the same. And that is why, because of this property only, this whole this whole spectroscopy is based upon. That is why we are able to identify the functional groups, because we know that the properties of the, I mean, the infrared spectrum of the functional group would not be influenced by the base structure to which they are attached. Okay, so this is important. So infrared UV visible spectroscopy and infrared spectroscopy, these are the two spectroscopy techniques that we have studied a little bit in detail in this chapter. So UV spectroscopy was easier, absorption emission, when an electron is going from a ground state to energy state, and infrared spectroscopy is also simple only, but you have a little bit more conditions, that the molecule should be active and how to identify the functional groups and the infrared spectrum. So basically, that would be outside the capability of this lecture, but understanding the infrared spectrum is also one another important thing. Okay, so infrared spectrum understanding requires some great knowledge of the different structures and everything. So I think it was there in your this thing course. So you can just go through it and you can just see how to identify the infrared spectrum. You can, through Google also, there would be very some examples, and I think in the course also sir has given one NPTEL course from where you can go and read about a little bit more detail about the spectroscopic techniques. So spectroscopy is a very important and a very has a lot of applications, and it's like its importance will, it's not going to die soon. It is going to be relevant, it is still going to be relevant, it is only going to evolve. Okay, so spectroscopy will be relevant for a very long time even now. So you should have a very basic and a clear understanding of what spectroscopy is, because I did my PhD coursework last year, and even up till PhD I had to study about how to study infrared spectroscopy, spectrum, and all. So what I'm trying to tell over you, that if you are from bachelor's or even if you are in masters, spectroscopy is not going to leave you. Not just spectroscopy, whatever we have studied in this module, in this lecture, and in other lectures also, these are very important topics. Spectroscopy will always come, and it haunt most of the students because students are not able to understand what spectroscopy is. So I have tried to explain you spectroscopy in a very basic and a simple manner. Just go through the slides. If you have any questions, you can just comment and tell me. And so I think this was a helpful class. And if you have any doubts, you can ask when it is uploaded. Um, I'll just quickly go through to see whether any point is left or not, and then I'll just end the recording. Okay, we have studied all this we have completed. So you can see this is for your UV visible spectroscopy. You can go on this link and you can just have a look at what this course says. It would be helpful for you only. Okay. Okay, this also we have studied. Okay, I think we have covered almost all the important topics. We have revised also, and we have discuss the questions also. So I'm just checking if I left something by mistake, some points. Um, yeah, no, I think things are covered now. Okay, fine. So, hope this was a hopeful, but it was a good class for you. Some informative and some knowledge gaining class. So, we'll wind up the class now. So, thank you. Bye.